Okay, so what we talked about all last week at kind of a breakneck pace was the quantum mechanical model for electron configurations and how to determine what those configurations are for specific atoms. We do have another homework assignment on Chapter 2, so in the event that last week felt like a rush, which it probably did for many of you, you'll have another chance to practice all this stuff on the homework assignment that's due next Sunday. So we'll spread it out a little bit in that regards, and you'll have more time to get questions answered and figure out some things. But we're going to move forward into Chapter 3, try to stay ahead of the homework assignments as much as we can. And today we're going to start talking about ionic and covalent bonding. So we talked about individual atoms and what their electron configurations are and how the electrons are arranged in atoms. And now we're going to start talking about what happens when two or more atoms combine to form a bond and make molecules or other types of interactions that would form compounds. So we're now moving into talking about actual chemistry as opposed to just the structure of the atom. So the first thing we're going to talk about are ionic compounds. So we did the bonus quiz. That's all done. So we're going to predict which ions are formed based on the periodic table. So one thing that the electronic configuration and the location on the periodic table helps us to do is to determine what the likely ions are that are forming. So when we're forming ionic compounds, one atom is going to completely lose one or more electrons, another atom is going to completely gain one or more electrons, and those charged ions are going to interact to form a compound. And we want to know what are the ions that different elements form. All right, so the ones that we should be most familiar with are what are called the main group elements, the ones that we talked about being in the S and P blocks of the periodic table. So Group 1A, these are numbered in a couple different ways. We'll talk about group numbers a little bit more today to try to clarify this. Your periodic table has Roman numerals, but you'll often see them with regular Arabic numerals, so you'll see them both ways. But Group 1A, and this is the older naming system, is going to be this first column of the periodic table. And so remember that in this group of the periodic table, there's going to be, for the valence electrons, there's going to be one electron in an s orbital. It's going to have an S1 valence configuration. All right, so Group 1A is S1. And then when atoms are going to gain or lose electrons to form ions, what they really want to do is form the electron configuration of the nearest noble gas. So they want to have that filled S and P subshells. It's a very stable configuration. So the atoms over here, if they lose one electron, they're going to have the nearest noble gas configuration. So if lithium loses one electron, it'll have the same configuration as helium. If sodium loses one electron, it'll have the same configuration as neon. So by losing one electron, they form the nearest noble gas configuration. So all of the elements in this column of the periodic table are going to form +1 cations, and there's really no exceptions for this entire group. So there's lithium plus, sodium plus, potassium, rubidium, cesium plus. So all of those Group 1A ions are going to form, atoms are going to form +1 ions when they make compounds, and there's really no exceptions to that. And then Group 2A just has an additional S electron. It has an S2 configuration. And so logic would hold then if these lose 2 electrons, they're going to form the configuration of the nearest noble gas. So these form +2 cations. So metals tend to form cations. That's another pattern we'll see. And these are the two groups of main group metals that we're going to be working with the most. And so all of the atoms in this column of the periodic table, all the elements form +2 cations. Beryllium, magnesium, calcium, strontium, and barium. So your book has tables of all these ions, but really, especially for the main group ions, you don't need to memorize anything because just based on the location of the periodic table, we can automatically tell whether it forms a +1 or a +2 ion. Now, if we go into the nonmetals, so we're going to go to Group 5A, 6A, and 7A, that would be starting, so 5A is going to be the nitrogen column, 6A is going to be the oxygen, 7A is going to be the fluorine. In this case, the easiest way to get to the noble gas configuration is to add electrons. So if nitrogen adds 3 electrons, it has the configuration of neon. If oxygen adds 2, it has that same configuration. If fluorine adds 1. So the nonmetals, the atoms on the right-hand side of the periodic table, tend to form negatively charged ions when you form ionic compounds. So Group 5A has an S2 P3 valence configuration, and by adding 3 more electrons to that P subshell, that outermost P subshell is going to have the filled S2P6 configuration. So they're going to add 3 electrons to form -3 anions. And the two that do this, so as we move down the column in group 5A, you tend to get from more non-metallic to metallic behavior because you cross that staircase, that divider line. But at least for the top two elements in group 5A, nitrogen and phosphorus, you can make these 3- anions. These are all the non-metals tend to form anions. And then 6A is the same story. We have an S2P4 configuration. And so by adding 2 electrons, you're going to get to the S2P6 valence configuration for a noble gas. So these would form -2 cations. And so oxygen, sulfur, and selenium would form -2 anions. And then finally, group 7A, the very common component of ionic compounds, has an S2P5 valence configuration. We call these the halogens, as we talked about last time. And by adding 1 valence electron, they're going to form an S2P6 stable configuration. So they would tend to form -1 anions. And all of them do this in this column, F-, Cl-, Br-, I-. Okay? So pretty predictable for these main group elements, based on their location on the periodic table, what kind of ions they form. One other one we should be aware of, I don't have it in this table, but there's one more in group 3A. Aluminum tends to form 3+ cations. So it has this would be 3s. There's a 3s2, 3p1 configuration as a neutral atom. And then if it loses 3 electrons, it gets to the neon configuration. Okay, so aluminum forms 3+ cations. That's another one you should be familiar with for ionic compounds. And for these elements here, all these main group elements, there's really no exceptions. Oxygen is always going to form a -2 anion if it's by itself. Nitrogen is always -3, magnesium is +2, and so on. So you don't have to worry about any exceptions to what I show you here for these specific elements. Now let's talk a little bit about the configuration of main group ions. We've kind of made reference to this as I built up this table, but the idea is that for anions we're adding electrons, and for cations we're subtracting electrons, and all the anions we're going to be talking about are in the P block of the periodic table, the nonmetals. And so which subshells do the electrons get added to when we add additional electrons? They're going to go into whatever the next available position is in that subshell. So when we do the electron configuration for anions, we're just going to continue following the Aufbau principle. Whatever the next available subshell is going to take that next extra electron. So for anions, we just add electrons to the partially filled P subshell. So remember, all those anions that we talked about on the last slide are in the P block. They have partially filled P orbitals in their valence configuration. So we're going to add electrons to that partially filled P subshell. So if we want to know the configuration of an anion, we start with the neutral configuration for the atom. So let's do oxygen as an example. So on our periodic table, oxygen is over here in group 6A. We just said it forms 2- anions. So the full configuration for oxygen is 1s2, 2s2, 2p1, 2, 3, 4. It's the fourth element in the 2p block. So the full configuration for oxygen is 1s2, 2s2, 2p4. And then if we want to make oxygen 2-, we add 2 electrons. And those extra 2 electrons are just going to go into whatever our available subshell is, which in this case is 2p. So the 2p subshell can hold a maximum of 6 electrons. So those extra 2 electrons are going to still go in there, giving a configuration of 1s2, 2s2, 2p6 for O2-, which is equivalent to the neon configuration, that very stable noble gas configuration. So when you're forming anions, you're just going to add those additional electrons to the 2p subshell that still has available spaces for 1 or more electrons. And then for S block cations, which is what we're going to talk about primarily, I don't think we'll deal with transition metal cations in this course. It's a little bit different for those. But for S block cations, group 1A and group 2A, we just remove those outermost S electrons. So when you're forming cations, you can almost think of, there's a rule called last in, first out. So the last electrons that you put into the atom are the first ones that you're going to remove when you form a cation. It doesn't always work that way, but so we're going to remove the outermost S electrons, that is those with the highest N value. All right, because as we talked about, the electrons that are in the highest value of N, the highest principal quantum number, they're going to be the ones that are furthest away from the nucleus. They're going to be held less strongly to the nucleus. They're going to be the easiest ones to take off if we're forming a cation. Okay, so that means if we have sodium, let's start with that simple example. The full configuration for sodium is 1s2, 2s2, 2p6, and then 3s1. So all these group 1a cations have a single electron in a valence s orbital. And if we want to make a cation for this, we said that we can remove one electron, and that's going to get us to the nearest noble gas configuration for sodium plus. So remember, when we form cations and anions, we don't change the number of protons in the nucleus, we only change the number of electrons. So this gets us to a 1s2, 2s2, 2p6 configuration, also the neon configuration. So that 3s electron, which is the last one we put in for sodium, is the first one we remove when we want to make the sodium cation, which would then also have the configuration of a noble gas. Now, another thing we need to talk about, which is very much related to things we dealt with last week, are the sizes, the radii of anions and cations. So when we start adding and removing electrons, how does that affect the size of the atom as we do that? So when we make cations, we know that we're removing the outermost electrons. So those electrons that are furthest away are the ones that we're taking off. So it stands to reason then that the cation is going to be smaller than the neutral atom. We've removed the electrons that are furthest away from the nucleus, so now the rest of the electrons are going to be closer to the nucleus. We're going to have a smaller species. So cations are always smaller than the parent atom, the parent neutral atom. And in some cases we can form, especially for the transition metals, which we won't talk about in detail, but for some cations, for some atoms, we can form more than one cation. So in the case of group 1a and group 2a, they're always going to form +1 or +2, no exceptions, but some atoms can form more than one different cation. And so if you're comparing ones that have different charges for the same element anyway, has a higher positive charge, it's going to be smaller. So the more electrons you remove, the smaller the cation is going to be. That sounds pretty reasonable. So one example of this, which we'll touch on a little bit later on, is lead, Pb. So lead can form both 2+ and 4+ cations. This is one of those examples where it can form more than one cation that's stable. And so lead is going to be bigger than lead 2+. As you remove the first 2 electrons, that's going to be smaller than the neutral atom. And if you remove another 2 electrons to make lead 4+, it's going to be even smaller. So as you remove more and more electrons, you're going to get smaller and smaller cations. Anions is the opposite story. So you add electrons to the outermost subshell, they're going to be larger. Now this is not because we're adding electrons to new subshells. So remember that when we form anions, we're adding electrons to the valence subshell. So we're not adding them to a higher quantum number n, but we have more electron-electron repulsions now. So as you try to cram more electrons in there, they're going to repel each other more strongly. They're going to want to spread apart a little bit to relieve that repulsion. So the anions are going to be larger than the parent atom. This is going to freeze on me again, isn't it? Alright, it's coming back. I think it's this video recorder that's bogging me down a little bit. Okay, so the anions are larger than the parent atom, and the reason is that adding electrons to the outer shell and so we're going to increase the electron-electron repulsions. Alright, so in the case of cations, we're completely removing the outer shell, so that's why they shrink. For anions, we're still adding electrons to the same subshell. So we saw that when we formed the O2- anion, we went from 2p4 to 2p6. So the electrons are still in the same subshell, but because there's more of them, they repel each other and sort of spread out a little bit to not be strongly interacting with each other. And then we also have this situation called isoelectronic atoms or ions. And so sometimes it's very possible to have atoms and ions that have the same number of electrons, in which case it would have also the exact same configuration. So you can have two different ions that have the same configuration. And so if we're comparing the radius of these ions, the positive ions, the more positive ions are going to be the smallest. If you have a neutral atom, that's going to sort of be in the middle. If you have an anion or negatively charged ion, that's going to be the biggest. So if we're comparing species that have the same number of electrons, if you have more positive charge, that means you have more protons in the nucleus, you're pulling those electrons closer. If you have more negative charge, that means you have less protons in the nucleus, those electrons are not going to be pulled as closely to the nucleus. So an example of this, of these isoelectronic cations, ions in atoms, if we have calcium 2+, let's start with that one. So calcium 2+, calcium is here, so calcium 2+ has the argon configuration, and so would potassium plus. So if we have calcium 2+ and K+, those both have the same electron configuration. They both have 18 electrons and they have the argon configuration. So potassium 2+ is going to be smaller than K+. They have the same number of electrons but different numbers of protons. Those have the same number of electrons as argon itself, which is going to be sort of in the middle. And then if we go to the nonmetals, Cl- has also the same number of electrons, 18 electrons. You add 1 electron to chlorine, you get the argon configuration. And then S2-, add 2 electrons to sulfur, you also get the argon configuration. So all these different species have the same number of electrons, and the ordering of the radii is going to be from most positive to most negative, from smallest to largest. All right, so the more positive charge you have on the ion, the smaller it is. If the electrons are the same, the more negative charge you have on the ion, the larger it is if the number of electrons are all the same. Okay, so this is a series of isoelectronic species, and that's how we would order the radii for those. All right, so now that we sort of know how we form ions, we can start talking about how do they pair together to make compounds, and what are the formulas of those compounds. So when we make an ionic compound, we're going to take a positive cation, and we're going to pair it with an anion of either the same or different charge, and we have to pair those up in the right ratio to make what's called a neutral compound. So when we pair up cations and anions, the charges must be balanced. We can't have any net charge in our ionic compound. So there's no net positive or negative charge when we form an ionic compound. All right, so a very simple example of this is if we have a sodium cation, we know that's going to be a +1 cation, and we combine that with a Cl- anion to make an ionic compound. We need to have exactly one of each to make a neutral compound. So the +1 charge on the sodium balances the -1 charge on the chloride, and we get NaCl, simple formula there. So whenever you're combining cations and anions to make a compound, you need to make sure that the charges are balanced. So then when we're writing the formulas for these compounds, the subscripts for ionic compounds need to have the smallest whole numbers possible. All right, so I gave you the formula for sodium chloride, which you probably all already know, which is NaCl. That's 1 sodium, 1 chlorine. We could also balance the charge, so we write it as Na1Cl1, which is written as NaCl. So if we don't have any subscript there, you assume that it's 1. We don't put subscripts of 1. But we could also, balance the charge by having 2 sodiums and 2 chlorides. This would be a neutral compound, Na2Cl2. We could have Na3Cl3 and so on, but these are not correct. When we're writing the formulas for ionic compounds, we always want the smallest ratio that gives us a balanced charge, in this case 1:1. So you never want to have subscripts that can be reduced down to smaller numbers. They have to be whole numbers, but they can't be anything, they have to be the smallest possible values. All right, so let's do a couple of examples of how we pair cations and anions together. So if we have calcium 2+ and O2-, those have the same charge, so it would stand to reason there's going to be one of those also. But there is a shortcut to this if you don't feel like doing simple arithmetic in your head. So if we have calcium 2+ and O2-, if we know the charges of the anions and cations, we can take the charge on one and make it the subscript on the other. So we crisscross them like this. So the 2 goes down there, the 2 goes down there. So that would give us calcium 2O2, which we recognize is not the lowest whole number ratio, so to simplify it further, we make it CaO. All right, so we don't feel like doing simple arithmetic to keep track of charges. You can take the charges and make them the subscripts on the opposite species, and that'll give you the balanced charges right away. And so sometimes it's a little bit more helpful, especially if the charges are different. So if we have this second example here, calcium 2 plus and N3 minus, we take the charge on calcium and make it the subscript on nitrogen. We make the charge on nitrogen and make it the subscript on calcium. And so that gives us calcium 3 N2, which we can't reduce any further without having fractional numbers. So that's how we get the formula for that one. We can verify that the charge is balanced. So for calcium, the subscript 3 tells us that we have 3 calcium cations. We know that they each have a charge of +2. So we have a total +6 charge from our cations. And then for the anions on nitrogen, we have, our subscript tells us we have 2 of them. Each of them has a -3 charge, and we get a -6 charge from the anions. So that, no, there's a mouse up here. That was not my most masculine moment. Sorry. All right, he's okay. It's just a mouse. We're going to be fine. So the charges do balance. We have a +6 from our cations and a -6 from the anions. I don't know if he came down to you guys, but he's somewhere under here as last I saw him. I think he's not. I think he's staying up here with me. Don't worry about it. All right, let's refocus. All right, this is not biology. Someone from biology class left their mouse in here. It's okay. All right, so we have, this is going to be the charge for calcium and nitrogen combined together. We'll talk about how we name those things a little bit later. All right, so now we've talked about ionic compounds, and for now we're just going to worry about these aspects of them. Now there is a section in your book that I should point out now, if you're following along with the book, about it's called lattice energy, Born-Haber cycles, which is section 3.4, I believe. We're going to skip that for now. So you shouldn't see any homework problems on that, and we'll cover that later on in chapter 7. We're woefully unprepared to deal with that, so I'm not sure why the book has it in there at all. So there is a section in your book we're skipping for now. So for ionic compounds, we're going to end with this for now. We'll talk about nomenclature a little bit later, but let's move on now to covalent compounds. So covalent compounds are going to be formed, as we'll talk about. Here he is again. All right, well, covalent compounds are going to be formed from 2 nonmetals together. So an ionic compound is going to be a metal with a nonmetal. The metal forms a cation. The nonmetal forms an anion. I think he's out, and he's gone. All right, hopefully he stays back there. Okay, so the people in the front got a glimpse of the mouse that's been haunting me for the last few minutes. So now we're going to talk about covalent compounds, and we have to talk about first covalent bonds. So covalent bonds are typically formed between 2 nonmetals. And the idea here is that for a covalent bond, we have 2 electrons that are going to be shared. So instead of having, one atom lose an electron, another atom gain an electron completely, the 2 atoms are going to be a little bit nicer, and they're going to share those electrons with each other. So first, let's talk about a bit of an energy level diagram for forming a covalent bond and why they form to begin with. So let's do it just for a simple case where, let's say we have 2 atoms. These could be hydrogen or anything else. And when they're really far apart, the 2 atoms have no interaction. So we're starting in a situation where they're far apart and have no interaction. And so when you're far apart and you have no interaction, the energy is still 0. There's no energy of interaction. Now, as these 2 atoms get close to each other, the electrons on one atom are going to start feeling the protons in the other atom. Remember that they want to be attracted to each other, so there's going to be an attractive interaction between the electrons on this first atom and the protons in the second atom, and vice versa. The electrons on this second atom are going to be attracted to the protons on the first. So they start interacting with each other, the electrons in one, the nucleus in the other, and so we get this electron-nuclear attraction as they get close enough together. And so the energy starts to drop. Because we've talked about this a little bit in some other contexts, is you have an attractive interaction that's going to be a a stabilizing interaction where the energy goes down. And so eventually you're going to get to what's called a stable covalent bond, which is the place where you maximize those attractive interactions, where the nucleus of one is now attracted to the electrons of the other and vice versa. So you get sort of this minimum energy here, and then the energy starts to go back up again, and goes up and up and up and up as you bring them closer together. So basically this x-axis here is how far apart they are. We're starting on the right very far apart. We bring them close together. At some distance they're going to have the maximum attractive interaction, and then as you get them too close to each other, the electrons and the nuclei start repelling each other because they're just in too confined of a space. So eventually repulsion wins out and the energy goes back up. So when you form a covalent bond, you're going to have some minimum value of the energy where those nuclei are just the right distance from each other to maximize the attraction between the electrons and the nuclei. And as we're going to talk about in detail on the next slide, the shape of this well, we call it an energy well, because it has sort of this concave shape. The shape of this well correlates with certain properties of the bonds that we're going to talk about. All right, so how deep this is in energy. So we have, how deep this well is, the location of the minimum on the x-axis. All those relate to certain key properties of a covalent bond, which we're going to get into now. All right, so the properties that they relate to then are called bond energy and bond length. So as the name suggests, the bond energy is a measure of the energy of interaction between two atoms as they form a covalent bond. So this will also be referred to as the bond strength. Or you might hear it referred to as bond dissociation energy. All these things sort of mean the same thing. All right, and basically this is the amount of energy that's required to break two atoms apart when they're bonded to each other. Now, it's actually the energy for 1 mole of a bond. We haven't really defined a mole very closely yet, but it's not just a single bond. It's a whole collection of those bonds, a huge collection of those, in the gas phase. All right, so we won't get too hung up on units yet, but it is per mole of bonds. But it's the amount of energy that it takes to break two atoms apart when they're bonded to each other. And so the chemical reaction we can think about is if we have two atoms, A and B, bonded to each other in the gas phase, how much energy does it require to break these completely apart to make A atoms and B atoms? And this change in energy is what we call the bond energy. The change in energy between the reactants and the products, between the left and the right side of that. So we call that the bond energy for AB, and that's always going to be a positive number. It always requires energy to break two atoms apart when they're bonded to each other. Okay? So that's the bond energy, and then how does it relate to this potential energy well that I showed you on the previous slide? That's going to be the Y value here. All right, so this Y-axis is energy, and so the point on here where we reach the minimum, that's the negative of the bond energy. All right, because if we want to go from bonded atoms all the way to free atoms, which is all the way on the right side, we have to have that much energy added to the system. It corresponds to the depth of the well. So how deep the well is going to tell you the bond energy or how strong the bond is. And then the other thing is that the other important parameter is bond length. This is the distance between the nuclei. So if we have the two atoms A and B bonded to each other, let's say the atoms themselves are different sizes, but it's this distance here, the distance between the two nuclei for A and B. Okay? And the important point here is that it's inversely related to the bond energy. So in other words, the shorter the bond, typically the higher the bond energy, the longer the bond, you're going to typically have a smaller bond energy. And on this diagram here, this is going to be the bond distance, the x-axis value where that minimum is reached. Okay? All right, so those are the key properties of a covalent bond we want to be interested in are the bond energy and the bond length. How far apart the two atoms are when they're bonded to each other, and how strong is the interaction between them. And as I said, generally speaking, there's an inverse relationship. Now, some other properties of a covalent bond that aren't going to be directly read from that diagram, an important one is called the bond order. So as I mentioned, a covalent bond is formed when two electrons are shared between two different atoms, but it's often possible for atoms to share more than two electrons. So it's the bond order is the number of bonding pairs between the two atoms. So each bond is a pair of electrons, and it's sometimes possible for two atoms to form more than one bond together. So it's the number of bonding pairs. All right, so a single bond is what we'd say the bond order of 1. So when we say that we have a single bond, that means the bond order is equal to 1, and that means there's one shared electron pair. All right, at the end of this week, we'll start learning how to predict the bond order for different combinations of atoms. But an example of this is hydrogen. Now, hydrogen only has one electron, so it can only form one bond with another hydrogen atom. There's only 2 electrons total. So you draw these single bonds as just a single line between the two atoms. Or sometimes you'll see them drawn as 2 dots. So a single bond has 2 electrons that are shared, so each of these dots represents an electron. There's 2 different ways of drawing the same thing. A double bond means the bond order is 2, and this is going to be 2 bonding pairs of electrons. So an example, which we'll learn in more detail at the end of the week, is oxygen bonded to itself forms a double bond. So when you see a double bond, it's going to be 2 lines in between the 2 atoms representing 2 shared pairs of electrons. If you draw out the individual electrons, which is not as common but is sometimes done, you'll have to draw 4 dots because there are 4 total electrons that are shared between those 2 atoms. And then the highest bond order that we'll see in this course is a triple bond. Bond order equals 3. You can go higher than this with transition metals, but that's a topic for the other course I teach, not this course. So if you're interested in quadruple bonds, you can come learn about them in my other course, but not here. All right, so bond order of 3 is 3 bonding pairs, and of course you just draw it as 3 lines, or 3 pairs of dots in between them. Now the bond order is also related to the bond energy, or the bond strength as we call it. All right, so the higher bond order gives us a shorter bond. So the more electrons that are shared, the more that those 2 nuclei are going to be pulled together, and that's going to correlate then with a stronger bond or a higher bond energy. All right, so that's another factor that influences the bond length and the bond strength is the bond order. So there's a direct relationship between bond order and bond strength. There's an indirect relationship between bond order and bond length. Okay, so we want to become familiar with those patterns for different chemical bonds. Now, because we're running low on time, I'm going to skip this problem, but I'll encourage you to do it on your own, and I'll have the solution in the notes when I post them on Blackboard. But for now, we have one more concept to cover today, which is electronegativity. So electronegativity is a property of atoms when they're forming bonds with each other, and it's very much related to ionization energy and electron affinity, which we talked about last time. So those are 2 properties of individual atoms, which are related to the position on the periodic table. Electronegativity also has a periodic trend, but is specifically a property of atoms when they're bonded to other atoms. And the definition is that it's the relative ability of a bonded atom to attract shared electrons. All right, so when we say that 2 atoms form a covalent bond and they're sharing the electrons, they're not necessarily sharing them equally. All right, some atoms want electrons more than others, so the electrons are often going to be pulled closer to one atom versus the other. And electronegativity is a measure of that. How much do these atoms attract the electrons when they're bonded to other atoms? So there's a scale for electronegativity. It's a relative scale, so it doesn't have any units associated with it. And it was derived or developed by Linus Pauling, a very famous chemist who spent most of his career at Caltech. And we should be a little bit familiar with the scale. We're not going to ask you obviously to memorize individual electronegativity values or anything like that, but we should be familiar with the extremes at least. So the highest electronegativity is going to be fluorine, which has an electronegativity of 4.0 on the Pauling scale. So that's the biggest value that you have. And the lowest is going to be cesium and francium on the other complete opposite extreme of the periodic table in the lower left, which have electronegativities of 0.7. All right, so it's not a very wide scale. It goes from 0.7 to 4. So there's a lot of elements, a lot of atoms that have very similar electronegativity values, but there is a scale and there is a pattern for it. And so the pattern comes directly from the periodic table, and because it's so much related to ionization energy and electron affinity, it has the exact same trend. So if we want to look at the trend for increasing electronegativity, it's up and across, just like it is for ionization energy. So as you go from bottom to the top on the periodic table, these become more electronegative, which means they're going to attract shared electrons more strongly. And as you go from left to right, you're going to have an increasing electronegativity. Now, the one exception to this, the noble gases don't have defined electronegativity values because they don't tend to form bonds with other atoms. But for all of the other atoms on the periodic table, they have a measured electronegativity value. And the highest one, as I said, is fluorine, which is up here in the top right of the periodic table. So that's going to be the highest value, and they increase going up and going across left to right. All right, and of course it's related to the size of the atom and the nuclear charge and all those things, just like ionization energy and electron affinity are. Okay, so it's going to be the same trend as electron affinity, which is a very closely related parameter. So electron affinity is the affinity of a single atom for an extra electron, and electronegativity is the affinity of an atom for an extra electron in a bond when it's bonded to something else. So they're very closely related and they have the same basic trend. And the electronegativity trend is actually probably smoother even. There's really no major exceptions to this trend, especially in the main group elements. So if you compare two atoms that are right next to each other on the periodic table, the one on the right is going to have the higher electronegativity value, and the one on the left is going to be smaller. If you're comparing two atoms that are vertically related in the periodic table, the one that's below is going to be smaller electronegativity, the one that's above is going to be higher. So there aren't really any major exceptions to this trend that you have to worry about, especially for the main group elements, which is mostly what we're going to be talking about anyway. All right, and so this introduces a topic called bond polarity. And so as I mentioned, when two atoms are bonded to each other, they don't necessarily share the electrons equally, and this occurs when the electronegativity values are different. So when we have two atoms bonded to each other with different electronegativities, so En is the electronegativity, and when these two atoms form a bond, the bonding pair, or pairs, depending on if it's a single, double, or triple bond, the bonding pairs are shared unequally. All right, so the way that we indicate this, if we have two atoms that have very different electronegativity values bonded to each other, we can show that the bond is what we call polarized, which is that the electron density is more localized towards one atom than the other. It's not exactly in the middle. So if we have hydrogen and fluorine bonded to each other, hydrogen has an electronegativity of 2.1, and fluorine, as we said, is the highest, is 4.0. So whenever you have two atoms bonded to each other with different electronegativities, or more rigorously, whenever you have two different atoms bonding to each other, there's going to be some polarity to the bond. And one way to draw this is to show it as an arrow that we call a dipole. All right, so you draw a little cross, and you have an arrow that points towards the other atom here. And so the arrow points towards the more electronegative atom. Now, perhaps a more instructive way to think about this, and probably the more common way to draw it, is that when you have atoms with different electronegativities, the atom that has the higher electronegativity is going to draw the electrons in more closely to it. And the reason we call it a dipole, or a polar bond, is because that means you're going to have one side of the bond is going to be a little bit more negatively charged, and one side of the bond is going to be a little bit more positively charged because the electrons are pulled more closely to the more electronegative atom. The net charge is still 0. There's not an overall charge for a covalent bond, but you still have more electron density over here than here. So a more common way to draw this, if you have a polar bond, is you have a little delta plus on hydrogen and delta minus on fluorine. So another Greek letter to learn, lowercase delta. And that means you have a partial positive charge on hydrogen, a partial negative charge on fluorine. It's not an ionic compound, so you don't have a full negative charge and a full positive charge, but there is some imbalance in that charge. It's not shared completely equally. And this is the more common way to write them, so you'll probably see this more often on the homework assignments. And it tells us that we have a partial negative charge on the more electronegative atom. Alright, so whenever you have a bond polarity, that partial negative, that delta minus, is going to be on the more electronegative of the two. Alright? And so the importance of this is that if we have different electronegativity values, and we take the difference of those two values, that tells us then about the nature of the bond and how polar it is. So if we have this delta En, this difference in electronegativity, for two atoms bonded to each other, A and B, it's going to be the absolute value of the electronegativity of A minus the electronegativity of B. So if we take the difference in the two electronegativity values, that gives us this delta En value, as we call it. And so if you have a perfectly covalent bond where the electrons are shared perfectly equally, no disbalance of charge, that only occurs when the difference in electronegativity is 0. So if you have two elements with the exact same electronegativity bonded to each other, then you will have no polarity in your bond. The electrons will be perfectly shared. This is only true rigorously when the two atoms are the same. So if you have two hydrogens bonded to each other, the electrons will be shared perfectly equally. If you have two oxygens bonded to each other, the two electrons will be shared perfectly equally. Now there are some cases where two different atoms have very similar, almost the same electronegativity values. So in that case, the bond would be fairly nonpolar as well, but it's only rigorously true if the atoms are exactly the same. And so we call these bonds nonpolar. When the electrons are perfectly shared, when the two electronegativities are exactly the same, we call that a nonpolar bond. And then polar or ionic bonds occur when the electronegativity value is different. So by convention, or sort of by approximation, if this difference in electronegativity is bigger than 0, but smaller than 2, we call this a polar covalent bond. And if the difference in electronegativity is greater than 2, we would classify that as an ionic bond. Now there's not really a rigorous cutoff here. This is, as I said, an approximation. So there's no real cutoff. So in reality, a continuum exists. So there's not really two different types of bonds. We like to classify them as covalent or ionic. But in reality, there's only one type of bond, and the only difference between them is how equally or unequally are the electrons shared between the two atoms. If they're shared perfectly equally, it's a covalent bond. In the extreme that they're not shared at all, you call that an ionic bond. But really, all bonds fall somewhere in between those two extremes. And so that's how I want to start thinking about them. Now, conventionally, as I said, if two nonmetals are bonded to each other, we call that covalent. If it's a metal with a nonmetal, we call that ionic. But there's really, the nature of the bond is the same for both, and it just depends on how equally the electrons are shared. All right, so I'll see you on Wednesday where we continue talking about these topics.